Hi, everyone. Thanks for having me very much, David and Carl. I'm going to be telling you about three, or if I'm lucky, and two if I'm not, short stories uh, due to these people who I'll introduce individually as we go along. And I do want to just mention that what I'm not going to talk about is what I've been talking about until recently, but I've decided I've been talking about this for too long. But if you're not familiar with it, um, we're working on the difference between tight balance and loose balance, the importance of being loosely balanced, and what we call the stabilized superlinear network, and how it can explain cortical response nonlinearities, suppression of cortical variability, attentional modulation. And if you're not familiar with this, I urge you to take a look at this review paper where we go through some of this in detail. But that is not what I'll be talking about today. And so today I have three stories, and the first one concerns the questions: does attention drive neurons that are tuned to the attended features or properties, or neurons that best drive high-level neurons representing those properties, or more generally, that are best for doing the task? And this is work that was done by Lindsay in my lab, and the whole approach is very much hers, her own creation. Grace is now a postdoc at what's it called, the Sainsbury unit in London with Mark Tom Merzig-Flogel and Manish Sahani. So what Grace did was she took a standard trained neural network. She didn't train it herself, and then she put on top of it, she trained a binary classifier to say yes or no, is a certain category present in the image. And she tested this on difficult images that were either transparent overlays of two images, which we'll call merged, or an array of four images. And whereas the binary classifier, using the already trained network, the binary classifier does very well on standard images, on the merged and array images, it doesn't do so well. And so this is a challenging task where attention might have some room to improve performance. And so we looked at what the tuning for properties across a given map. And so a map being a feature within a layer. So a layer might have, 256 different channels or features, and this is one of them, arrayed across space. And there were 20 categories that Grace was considering that were either binary detected, either present or absent. And you want to know, well, how does this particular map, on average across space, respond to images from these different categories? And that is the tuning value shown in green here, positive for some categories, negative for other categories. Here's another map, and here's another. And we also looked at the gradient value, which is the change in that map's activity, average across space, that you would need to most improve the classification performance of the binary classifier. And you see for some maps, the tuning for that category and the gradient for that category are nicely lined up. But for other maps, they don't have a lot to do with each other. And so when we look at the correlation coefficient between the tuning and the gradient, this is the shuffled control. We find it's a pretty weak correlation in the early layers. It only gets reasonably high toward the very end, toward the very top layers. So this already poses the question, well, maybe it would be smarter to attend in the sense of increasing neurons activity or decreasing neurons activity according to the gradient for the task you're doing rather than for the feature that you're attending to. So let's look at how attention affected performance. Attention was implemented as a multiplicative change or change in the gain, a multiplicative scaling of the rate according to either the tuning value or the gradient value. So where the tuning value is positive, you increase your response. Where the tuning value is negative, you decrease your response. And does this increase performance? Yes. If you look, tuning increases performance by a number of points, and a lot more points if you attend at later layers rather than at earlier layers. And the gradient, of course, does a lot better, particularly before you get to the very final layers. And that's true whether you're looking at merged images or the array of images. Okay, so did the same thing rather than for image categories. Gary, I don't know what I don't know what the question is, so I don't know what to say.
Yeah, are these changes in performance just by changing the gradient at that layer?
Right. So if I go, yeah, so at one layer, at the particular layer we're indicating, we apply attention and not at any of the other layers.
Okay.
And then we look at the performance increase according to what layer attention was applied at, either by tuning or by gradients. Thanks.
Thank you.
Yep. Okay, so now we're going to do the same thing, but for a simpler set of images, namely orientations of different colors. And here the task is to say, is a 20-degree grading present or absent? And again, you get a considerable improvement in performance with tuning and even better with gradients. And again, the correlation coefficient between tuning and gradients is even more poor than it was before, and in fact, negative for the early layers. And I should say one thing about the performance increase, which is that why would you get a performance increase? There's two things going on. You have false negatives that the attention is turning into true positives, and you have false positives that the attention might turn into true negatives. But you also have the problem of false positives. So true negatives that are being turned into false positives. You're enhancing activity that will drive that category. So you're going to increase the number of things that are categorized as that category, whether it's correct or incorrect. So in order to improve performance, the true positives have got to come up faster than the false positives. And that's what happens. What we find is that the true positive, the false negatives are sitting a lot closer than the true negatives and so when you increment it, the false positives come up first and you improve your performance. Okay, so this is the situation we're facing with orientation. And so we can look at how the attention propagates across the layers. Before I showed you the overall change in performance at the end, if I put attention in different layers, we can look at the propagation as follows. In a given layer, we're going to record from a given layer. We'll have applied attention in that layer or in some other layer, but only in one layer. And we'll record from a given layer. And this is following the feature similarity gain model of Troy and Martinez Trujillo. The idea is that you look at the categories you're looking at, like orientation 20 degrees, 30 degrees, 40 degrees, from most preferred to least preferred for that particular map or those particular neurons. And then you look at the difference between how that map responds to that category when you're attending to that category versus when you're not attending to that category. And so what you expect is that the category that the neuron or the map is most responsive to, it most prefers, that's going to go up because it's tuned for that when you attend to it. And the one that is least preferred to, it's not tuned for, it's going to go down when you apply attention for that category, because it's the ones that prefer that category that are going to go up, and the ones that don't prefer that category are going to go down. So this is saying when I attend to this category or to this category, how does my performance, or how does my activity change when I've lined these up by my own preferences as a map? And you characterize this change by two quantities: the slope, which we expect to be negative, and the intercept, the difference from one, which we expect to be positive. And so we now look at the layer recorded from what is the slope and intercept in that layer when we've applied attention at the layer indicated by the color. And what you see is if I apply attention in layer 2, I get a nice intercept and a nice slope, but it's pretty much gone by the time I get to the top of the network. So the influence has disappeared. And you see the same thing until you start applying attention somewhere around layer 10, when finally the attention propagates to the end. But before that, it pretty much fades away. And what that's telling you basically is that the neurons that are tuned for 20 degrees here are not necessarily driving the neurons that are tuned for 20 degrees here. because maybe they weren't specializing at 20 degrees. They just, when you look at your arbitrary set of categories, they happen to respond best to that one. But they're really doing something else, and they're really driving other neurons up here doing something else. And so attending to 20 degrees down here does not help you recognize 20 degrees up here. On the other hand, if we use the gradient values, you see that we get this, you don't see it for a long time, no matter what layer you apply it in. Again, the layer you apply it in is given by the colors. But then at the end, it shows up because you're applying it according to the gradient. And so by the time you get to the end, it should correctly modify the activities to drive recognition of that category. And so you can see that if the biology works anything like this, then it would be a lot smarter for the biology to use gradient values than tuning values, or more generally, to take into account the task and not just the feature that you're attending to do the task. And so Grace came up with a experiment to distinguish these two things. And the idea is that you're going to do two different tasks with the same attended feature. So one task will be a color classifier. And that is, you're looking for 20 degrees and you're seeing different orientation to colors, and you want to report the color of the 20 degree orientation. The other is what I showed you before. You're seeing various orientations and colors, and you want to report whether or not the 20 degrees is present or absent. And in the color task, again, actually it works the other way. The tuning and gradients are more poorly correlated at the end than at the beginning. But the main thing is when we look at the attentional modulation in these different tasks, if you're attending by tuning, if you're attending to 20 degrees, which is the thing you have to pay attention to in both tasks, then your attentional modulation is exactly the same no matter what task you're doing. But if you attend by gradients, then even though in both cases you're looking for the 20 degree grading to either decide if it's present or to decide what color it is, there's basically no correlation in the gradients for the task that you use to do the task. And so what we are proposing to experimentalists, and we might have someone who now wants to do this, I hope so, is to do this experiment, or experiment very much like it. Two tasks, two different tasks where you attend to the same feature, and if the attentional modulation differs for them, it doesn't necessarily mean biology is smart enough to use the gradients, but it means biology is smart enough to know something about the task when it applies attention, and not just do it by the feature you're attending to, and that's what we want to test. Okay, so that's story number one. Oh, and also, one last thought, how could either form of attention be achieved? So if you think about it, attention has to be, say, frontal cortex, some high up area is projecting back to lower areas and enhancing whichever neurons ought to be enhanced, or changing things however they should be changed. And so you have to ask, how would frontal cortex know which neurons in V2 are most sensitive to 20 degrees, or whatever arbitrary task you happen to have thrown at it at that moment, whatever arbitrary thing you told it to select to? It might, I don't quite know how it would know that. But if you ask, how would it know the gradient? That is, it wants to know the neurons down below that best drive those itself up above. The neurons that are best for the task want to drive the neurons that best drive the neurons that are best for the task. And that would be easy, in principle, if you had an anti-Hebbian learning rule, so that if these neurons fire and then these neurons fire after, then you reward those synapses back by an anti-Hebbian rule, and then you know which neurons down below fire you. So it seems to me, in principle at least, it would be much easier for the biology to learn to apply attention by gradients than it would to apply attention by tuning. You might disagree, but that's at least my thought. Okay, so I'll leave this one here and go on to part two, which was done by Agostina Palmigiano, a postdoc in the lab, who has done really an incredible tour de force of work that I'm not going to tell you all about. I'm going to tell you a little bit about, and with a number of collaborators working with Hillel Adesnik's lab, Dan Mossing in Hillel Adesnik's lab, who did experimental work that we're basing this on, and with Francesco Fumarola and Natalia Kranyukova, other theorists that we're working with. And you can find these in two preprints. This is the main preprint of the whole tour de force. This is a very short preprint just devoted to some specific low dimensional issues. So let me tell you about the story. So first of all, I want to distinguish low dimensional versus high dimensional models. By low dimensional, so we're going to consider the well-studied 4-cell type network of 3 inhibitory cell types, parvalbumin, somatostatin, and VIP expressing neurons, and excitatory neurons. And a low dimensional circuit model would have 1 unit per cell type, and you're just trying to model the mean responses. A high dimensional model will have many units of each cell type. And we're going to try to model not just the mean responses, but the entire distribution of responses, which isn't something I think that has been done much, if at all, before, to model the distribution and not just the mean in circuit models. And we're going to be, the way we characterize these high dimensional circuit models is the connectivity from one cell type to another, and the input to a given cell type is characterized by a mean and a variance. So it's going to be stochastic up to a cell type specific mean and variance. And we're only, for this talk and for the work in the preprint so far, we're only going to consider non-spatial models. So they're just a lump of neurons. They're not spread out in some organized way. And so we're just studying a local circuit, which we believe would be suitable for responses to small visual stimuli that don't activate an extended network. And so that's what we're going to focus on is fitting the responses to small visual stimuli. And so let's begin by considering low dimensional models. And as background, I want to remind you of what probably many of you know very well, the so-called paradoxical response in inhibition-stabilized networks. And this is something that Misha Sodix first pointed out in 1997, and then we brought back to life when we realized that this was an explanation for what was going on in David Furster's recordings of surround suppression in 2009. And the idea is as follows. So you have a low-dimensional model, excitatory cells and inhibitory cells, 1 unit representing each, with connections between them and to themselves. And you imagine that you're showing a center stimulus, and you're at a fixed point for the center stimulus. And now you add the surround stimulus. And what happens? And for simplicity, although the surround stimulus goes to both, let's imagine the surround stimulus only goes to the inhibitory cells. So the center stimulus is there, but I'm not showing it anymore. I'm just showing the surround stimulus that we've added. And what happens then, we add excitation to the inhibitory cells. The inhibitory cells raise their firing rates, and that lowers the firing rates of the excitatory cells. But now, 2 things are going on. We've added excitation to the inhibitory cells, but we're also subtracting excitation because they're getting less recurrent excitation from the network. So which of these is going to win? Well, if the excitation alone were unstable at the fixed point. Now, what do I mean by that? What I mean by that is sitting at the fixed point with the input coming in from the center. If I was to tick the excitatory rates up a little bit, they would recruit too much recurrent excitation. And so they'd want to keep going up. And if I tick them down a little bit, they would lose too much recurrent excitation. They'd want to keep going down. But if the inhibition can dynamically respond, the network itself is stable because the inhibition responds to that change in excitatory firing and brings the network back to the fixed point. So it's a stable fixed point. But if I froze the inhibition and didn't let it dynamically respond, then the excitation alone would be unstable. The network at the fixed point is being stabilized by the inhibition. That's what I mean by an inhibition-stabilized network. So if this is an inhibition-stabilized network, then when the excitation decreases, it's lost too much recurrent excitation to sustain that lower firing rate. And not only that, but it's receiving more inhibition than it was at the old fixed point. So there's absolutely nothing to break its fall. It wants to keep going down. There's nothing to stabilize it. And how will you stabilize it? You either have to add some new source of excitation to make up for the overloss of excitation, or you have to end up with getting less inhibition than you were at the fixed point in order to stabilize against the excessive loss of recurrent excitation. And so what happens is the excitatory firing rate keeps falling until this loss of excitation exceeds this loss of excitation. And the firing rate of the inhibition then goes down below the fixed point level. And at some point, when it falls enough, that ends up stabilizing. This is your new stable state. This is your new fixed point given this additional input. And you might have thought, well, now the excitatory cell is receiving less inhibition than it was at the fixed point. So now it's going to go up and I'm going to have an oscillation. But no, because it's lost too much recurrent excitation, that loss of inhibition is exactly what it needs to stabilize. And so this is the so-called paradoxical change in the inhibitory firing. You've added excitation to the inhibitory cells, and their firing rate has gone down in response in the new stable state. And that happens if and only if in this two cell type model, if and only if the excitation is inhibition stabilized at the fixed point. Now, you can see from the logic of what I just said what the general result must be if you have multiple inhibitory cell types here. The excitation has lost too much recurrent excitation, so it has to, if you haven't added any new sources of excitation, if you've only added input to inhibition, it has to be receiving less inhibition at the new stable state than it was at the initial stable state, at the initial fixed point. So the general result is not that any particular inhibitory cell type has to respond paradoxically, but that the net inhibition that the excitatory cell receives has to change paradoxically. If the excitatory firing rate goes up, the net inhibition it receives has to paradoxically also go up. If the excitatory firing rate goes down, net inhibition it receives has to also paradoxically go down. And we pointed this out as a qualitative statement in this paper, and completely independently, Ashok Litwin-Kumar with Robert Rosenbaum and Grant Doiron showed mathematically that that is the generalization in 2016. And I should say that this ISN effect, these paradoxical effects of activating inhibition and ending up driving inhibition down, have been shown now in multiple systems in multiple cortical areas. You can generalize this if you have multiple excitatory subtypes. Essentially, if you observe that all the excitatory types change their firing rates and their inhibition they receive in the same direction, then you know that it's an inhibition stabilized network, meaning that there's at least one mode of that excitatory subnetwork that is unstable. Now, if the inhibitory input to the excitatory cells decreases, of course, that means that some of the inhibitory cell types must have lowered their firing rates. But it doesn't have to be the one that you stimulated to start the process. So it doesn't have to be a paradoxical response, but some inhibition clearly has to go down. So what we're going to ask now is, when do you actually get a paradoxical response in firing rates when you have a multi-cell type circuit? And so our framework is looking at linearized response in a rate network. So we have a rate equation, some diagonal matrix of time constants times this is the vector of firing rates across all the neurons, excitatory and inhibitory in the network. And the firing rates are moving toward a fixed point, which is some nonlinear function of the input the neuron receives, which is the recurrent input, the weight matrix times the rates, plus the external input, which we'll call H. And so we're at some fixed point for some given H. And now we want to look at what happens around the fixed point. So we linearize and we get this equation for the change in rate from the fixed point and the change given the change in input, where F prime is the matrix of derivatives of this F function at the fixed point, the diagonal matrix of derivatives. So then your new steady state, you just set that to 0, and you bring this over, and it's multiplied by 1 minus F prime W, and you multiply by the inverse of that, and so you get that delta R is 1 minus F prime W inverse times F prime delta H, and you can rewrite that as F prime inverse minus W quantity inverse times delta H. And we're going to call this matrix multiplying delta H chi, the response matrix. So this is our linear response matrix. And a cell type I has a paradoxical response if and only if the II diagonal element of chi is negative, meaning that if I perturb chi, if I perturb I, the response of I is negative. If I give it a positive delta H, I get a negative response out of the same cell type. So when do individual cell types have a paradoxical response? This is repeating what I showed you. Well, let's write down the Jacobian of the system, which is the linear operator that's driving the dynamics of the linearized system. And you can see that this is, given that this is what chi is, this is negative T inverse times F prime times the inverse of chi. Or in other words, chi times F inverse times T is the negative Jacobian inverse. So we can write that in components, and since F and T are diagonal matrices, we just get the J components of those multiplying chi ij is the ij element of this. But we know there's a formula for the inverse of a matrix, so we know what the ij element of this is, and that is it's -1 to the I plus j over the determinant of negative j times mji, where mji is the minor, the ji minor of negative j, meaning that it's the determinant of the submatrix of negative j that excludes row j in column I. And so in particular, if we want to look at the diagonal element, which determines whether or not you have a paradoxical response, that is 1 over determinant of negative j times the determinant of the j matrix of the negative j matrix with that cell type removed, that row and column removed. So it's the determinant of the, it's the Jacobian of the circuit when that cell type is not dynamically active anymore, when that cell type is eliminated. So it's the Jacobian of the circuit without that cell type. And so now we know that for a circuit, for a fixed point to be stable, the Jacobian, all the eigenvalues of the Jacobian have to have negative real part, which means the determinant of the Jacobian has to be negative. Well, sorry, it depends on the dimension. But that means that all the eigenvalues of negative j have to have positive real part, which means the determinant of negative j has to be positive for the circuit to be stable. And so we know, we've assumed we're at a stable fixed point. So this is positive. So the sign of chi I is just the sign of the Jacobian of the circuit with that, the negative Jacobian of the circuit with that, the determinant of the negative of the Jacobian of the circuit with that cell type removed. And what that represents is if this is positive, then that cell type can be stable. Then the circuit without that cell type can be stable. But if this is negative, it means the circuit without that cell type is unstable. And so you get a paradoxical response precisely when the subcircuit excluding that cell type is unstable, and it has to have an odd number of unstable modes. If it has an even number, this will be positive. And that's peculiar. I don't have any intuition for why with one unstable mode you get a paradoxical response, but with two unstable modes you don't. And if anyone has such an intuition, please let me know. But at any rate, that's the math, that's the result, that when you stimulate cell type I positively, you get a negative response to it precisely if the circuit without it, well, if you do, not if, but only if you do, then the circuit without it is unstable. Oh yes, and has an odd number of unstable modes. So this is an if and only if odd number, but it's an if you just say that the cell type with the circuit without it is unstable. If you see the paradoxical response, you know the circuit without it is unstable. Right, so paradoxical response implies the subcircuit is unstable, but the subcircuit unstable does not necessarily imply a paradoxical response. And by subcircuit, I mean the circuit without the cell type you're thinking about. Corollary is that if you see a paradoxical response in parvalbumin cells, which have been seen by a number of groups, Marak et al. From David and Carl and others, and Sanzani et al., that is telling you that parvalbumin is stabilizing the circuit, that without parvalbumin, the circuit would be unstable. But as Marak et al. Pointed out, this paradoxical response itself does not imply the circuit is inhibition stabilized, that the excitation is inhibition stabilized. It implies PV is stabilizing the whole circuit, but it doesn't mean excitation alone is unstable. But if you stimulate PV and you see that all the cell types that project to E cells, namely PV and somatostatin, and all the E cells respond in the same direction, respond negatively, then you know that the inhibition received by E has paradoxically decreased, and so you know it's an ISN. So from stimulating alone, PV alone, you can tell it's an ISN if you also look at how the other cell types, inhibitory cell types, respond to that stimulation. And as an example, we're not used to thinking of excitation having a paradoxical response, but indeed it can if you cook up the right circuit. And this is not meant to be a realistic circuit. It's just a circuit we cooked up to show that indeed there's a circuit where If you now, at time zero, we're at a fixed point represented by the values at time zero of these different cell types. And then we give an input only to E, and you see that it lowers its firing rate in the new steady state. Okay, so that's low dimensional circuit models. So now we want to go on to high dimensional circuit models and characterizing how do they respond to perturbations. And Agostina has done an entire framework that I'm not going to tell you all about. I'm just going to mention, I'm going to tell you just some key points for what she's done. But the framework is as follows. You have a distribution of responses, in this case of every cell type across every contrast for small visual stimuli in a mouse, in this case in a stationary condition. And this is the data collected by Dan Mossing and Hillel Adesnik. And we want to fit a model to the entire distribution of all the cell type responses to all of the stimuli. And the way she does that is twofold. There's a formula from a paper by Alex Roxon and colleagues that says if you have a superlinear input-output function, a power law input-output function, which is what we believe characterizes these neurons, the basis of our stabilized superlinear network, then there's a closed form formula describing the distribution of responses that you will get in those networks to any given input. And so Agostina can use that closed form formula to fit an analytic formula to the data, and then she can use mean field theory. Given a set of means and variances of all the responses and all the inputs, she can analytically derive what the distribution of responses will be in the model. And then she can go through lots and lots of models and find the ones that match the data. She has two analytic forms, so she can just compare those analytic forms using a Kullback-Leibniz divergence and find a whole set of models that fit the whole distribution of the data very well. And then having this model, she can look at the response to perturbations. And she looks at a number of things. I'm going to focus on these two. The way that the low dimensional issue of subcircuit stability generalizes to the high dimensional circuit, and what happens if you're doing a partial perturbation, only stimulating 50% of the parvalbumin cells, not 100%. So again, this is just reviewing the framework from the low dimensional case, but this is actually a very general framework. The same for the high dimensional case, for all where F prime is the diagonal matrix of derivatives of all of the neurons in our high dimensional network, and W is the high dimensional set of connections. This is still the linear response network matrix. And so there's two things that are going to change the high dimensional case from the low dimensional case. One is that there's heterogeneity in the connectivity. The connectivity between any two cell types is randomly distributed with a given mean and variance. And there's also heterogeneity in the gains because there's heterogeneity in the firing rates of a given cell type. And what Agostina figured out she could do is that she could get an analytic formula for the high dimensional distribution of responses by making the following approximation. She neglects the heterogeneity in the gain, keeping the heterogeneity in the weights. And then she can analytically compute what the distributions of responses will be. And so she calls that the homogeneous fixed point approximation, neglecting heterogeneity in the neuronal gain. And it turns out that, so in that case, given a perturbation pattern, we can analytically infer the distribution of responses. And it turns out sorry, I'm getting ahead of myself. So if we do that, so if we simulate we being she, simulate the high dimensional, fully nonlinear case for perturbation of all the parvalbumin cells, 100% of them, you see that indeed all the responses of all the neurons are negative, or almost all. So this is the paradoxical effect. If you look then at the homogeneous fixed point approximation, it's not perfect, but it gives you a pretty good idea of what goes on in the fully nonlinear model. And so just from numerically verifying, we believe that this is a pretty good proxy for understanding what goes on in the full high dimensional model. And this is something we can analytically calculate. And furthermore, in the homogeneous fixed point approximation, the mean of the distribution is precisely the mean of the distribution in the low dimensional model. So the low dimensional model will now inform us on what our mean response is in the high dimensional model, to the extent to which this is a good approximation to this. And so if we look at the whole family of models that fit the data well, either in the, either in the homogeneous approximation, which is these turquoise color, or in the fully nonlinear simulations, which is this green color, we find they pretty well agree with each other. And across all contrasts, indeed, we're getting a paradoxical mean response of the inhibitory population. And you can also calculate the standard deviation across the population, the distribution of those responses across the parvalbumin population. So lesson number one is, for full perturbations, our low dimensional results carry right through in terms of the mean result, approximately, of the high dimensional case. And so the mean, in the high dimensional case, the mean response will be paradoxical. If it is paradoxical, it means that the circuit is unstable without those perturbed neurons. Right, and this is just repeating that point. But now, what about partial perturbations? So imagine you're only perturbing 50% of the parvalbumin cells. Well, what the analytics in the approximation show are that you get two Gaussian bumps of responses. One is the perturbed of the PV cells. One is the perturbed population, and one is the unperturbed population. The unperturbed population is always going to respond negatively because you're activating cells that inhibit them. The perturbed population, if you don't perturb too many of them, is going to respond positively. It's going to respond directly to that stimulation. But as you increase the fraction of cells that you perturb, the perturbed cells, their mean is moving more and more negative, because eventually, when you stimulate all of them, they're all going to have a negative response. They're all going to have a paradoxical response. And so for 100% perturbation, you get what I showed you before. They all have a negative response. And so if you now look at, if you're recording, which is often the case, if you're recording the parvalbumin cells without knowing which ones are being stimulated by the light and which ones are not, and you're just looking at how many parvalbumin cells respond negatively to the light, what you'll find is that for very tiny fractions, basically they all respond negatively, but it's going to be a tiny effect size. You probably can't see it. But at any rate, as you increase the percent of perturbed PV cells, the fraction responding negatively is going down, because all of the non-perturbed cells, always 100% of them are negative, and the perturbed cells, 100% of them are positive up to some point. And the more of them you stimulate, the bigger fraction of the PV cells are represented by these perturbed cells. And so the fraction with the negative response is going down until you get to the point, roughly, where, well, sorry, I'll get to that in a minute, sorry, but until you get to the point where the bump of perturbed cells starts crossing zero, and more of them now are having negative responses. And at some point in there, this turns around, and now it grows with increasing fraction of perturbed PV cells and goes back to 1 at 100% perturbed. And so Agostina calls this the fractional paradoxical effect, that if you don't know which ones are stimulated and which aren't, and you just look at how many have a negative response to the light, it's a non-monotonic dependence on the fraction of cells that you're stimulating. Right. So when we now look in simulations of the full nonlinear system in green, or the approximation in turquoise again, we find across all contrasts that we indeed see this fractional paradoxical effect, that going down before the going up as you increase the fraction of perturbed parvalbumin cells. And there's one more thing we can say about this, is that we can build a pseudo model in which there are 5 cell types. There's the perturbed PV cells and the non-perturbed PV cells and the other 3. And we know from our low dimensional analysis that the perturbed PV cells will have a negative response precisely, well, we'll only have a negative response if the circuit without them is unstable. So given that when you stimulate that the circuit without all the PV cells is unstable, what we know is that the mean, at least in the HFA approximation, the mean of the perturbed PV cells is crossing zero precisely when the subcircuit without that subset of PV cells becomes unstable. And so we know something about, how big a fraction does it take to turn around? It basically takes, well, to get the mean to cross zero, it takes a big enough fraction to destabilize the rest of the circuit without those cells. Okay, so that's story 2. I will try to quickly tell story 3 because I know I only have 4 or 9 minutes or something. And the third story is from Mario Dipoppa, another terrific postdoc in the lab, working with Massimo Scanziani's lab, and in particular, Andy Keller and Morgan Roth and Matt Caudill, who did the experiments, and also Alessandro and Ingrosso helped with the theory. And again, we're considering this 4-cell type circuit. And here I want to focus in a little bit more on the specific circuitry of that circuit. VIP basically only connects to somatostatin. I mean, it may have weak connections to the others, but the only strong connection is somatostatin. It doesn't connect to itself. And so that means it doesn't directly inhibit anything. It disinhibits. It inhibits the inhibitory, one of the inhibitory cells that inhibits the excitatory cell. And this disinhibitory circuit has been established in lots of systems now to activate excitatory cells and to be a source, a site of modulation, top-down modulation, that by modulating these VIP cells, you can turn up and down the gain of the circuit. So the Scanziani lab focused on what they call contextual modulation, the difference between an iso-oriented surround, one with the same orientation as the center, and a cross-oriented surround, one with the opposite orientation as the center. And what you can see psychophysically already the effect that the iso-oriented surround seems to lower the contrast of the center compared to the cross-oriented surround, which doesn't. And that's a psychophysical reflection of the neuronal fact that for excitatory cells, at least in layer 2-3 in the mouse, and in many other species has been shown, they are not suppressed. If anything, they're facilitated by the cross-oriented surround, but they're very much suppressed by the iso-oriented surround. It turns out in the mouse, this is much less true in layer 4. They're more weakly suppressed by a cross than by an iso, but they're suppressed by both. So this is an effect that emerges in layer 2-3, and we want to understand how it emerges in layer 2-3. And I just want to get you familiar with the way I'm going to show you the other cell types. Actually, ignore this one. But here, if we look at the response to iso versus response to cross, you see that the excitatory cells very much prefer the cross to the iso stimulus. And if we compute a contextual modulation index, which is the cross response minus the iso response over cross plus iso, that's positive when you prefer cross, and it's positive for almost all the excitatory cells. So now if we look at the other cell types, parvalbumin, VIP behave very much the same way. They like cross, they're very suppressed by iso. They have positive contextual modulation indices for the most part. The gray is showing you the distribution for the excitatory cells that I just showed you. But somatostatin is the odd man out. Somatostatin prefers iso and is facilitated by iso and is suppressed by cross. And so you see that, on the whole, somatostatin prefers iso to cross. On the whole, somatostatin has negative contextual modulation indices. And I want to just alert you, this is 280 neurons, so this is a pretty good sample. Later, I'm going to show you a smaller sample where the positive and negative are much more evenly distributed, but we think with this bigger sample that this better characterizes the somatostatin cells. So somatostatin is doing the opposite. This suggests a picture where when you're seeing the iso-oriented stimulus, somatostatin is responding well, and it's inhibiting everybody else. It also inhibits PV for that matter. And also by inhibiting excitation, you're inhibiting the excitation to PV. So all 3 other cell types are either getting inhibited or losing excitation. But when you see the cross stimulus, now VIP is winning and SOM is suppressed, and so excitation is disinhibited. And I should add, I mentioned that this is a disinhibitory circuit. At least in many, it isn't always disinhibitory, but in many systems, including layer 2-3 of mouse V1. But also that there's a competition between VIP and SOM because they inhibit each other. And so one tends to get the upper hand in some circumstances, and the other tends to get the upper hand in other circumstances. In this case, we see between ISO and cross, SOM gets the upper hand for ISO, and VIP gets the upper hand for cross. So this is a hypothesis as to what's driving things. And Mario went to test this hypothesis by developing a model. And the model is, we have these 5 cell type circuits counting the layer 4 inputs, and we have 4 of them, one for one orientation and one for the orthogonal orientation, and one for the center and one for the surround. And the connectivity as such has a symmetry so that all of these networks are treated equally. And Mario fit the data fit the model to the data, building a huge set of pseudo data found by perturbing the actual data according to the standard errors of the data, fitting with non-negative least squares, taking the best solutions and working with Alessandro Ingrosso to refine them with back propagation through time. And after all of this, arrived at 115 best solutions, which seemed clearly separated from a larger mass of poorer solutions. And so the resulting fit, so the red shows the data, and the colored shows the 115 solutions. Excitatory cells were fit pretty well. PV was pretty well. You can see not everything was fit perfectly. The models think that ISO is responding, SOM is responding less well to ISO than it actually does. And the models think VIP responds a little better to cross than it actually does, and thinks there's less of a difference between ISO and cross in layer 4 than there actually is. So the model's not perfect, and that you might worry about that, and certainly we worry about that, but these were the best fitting models. And so if we now analyze what's going on in the circuit, so we're sitting at the fixed point for the ISO case, and now we change the layer 4 inputs to the cross case. And what happens? Well, if we look in the plane of the somatostatin responses and the excitatory responses, we find that the somatostatin responses get suppressed, as you would expect for going from ISO to cross, and the excitatory responses accordingly grow. But over time, the somatostatin becomes less suppressed. It's a non-monotonic trajectory of the somatostatin, reminiscent of the paradoxical response. And if it was a paradoxical response to stimulating somatostatin, it would go down and in the end be positive. Well, it's not doing that, but it's going down and coming back up again, presumably because it's gaining more excitation because the excitatory cells are increasing their firing rate. So there's this non-monotonic trajectory. In the end, the somatostatin hasn't really changed its responses very much. And if you look at the change in the input to the excitatory cells, what you find is the major change is not a change in the somatostatin inhibition, but it's a change in the recurrent excitation of the excitatory cells onto themselves. There's a lot more firing of the excitatory cells, so they're exciting themselves much more strongly. You also see that there's a paradoxical response in the sense that the total inhibition, the PV inhibition has increased. It has a stronger negative input. The somatostatin inhibition has decreased, but not by as much. So as the excitatory firing rates went up, the inhibition they receive has gone up. It's a paradoxical response. But although somatostatin might be driving things, we're going to look at that in a moment, you don't see much trace of it in the final result. It kind of erases itself through this pseudo-paradoxical response, leaving, it basically catalyzes this increase in recurrent excitation. And to show this, Mario now did this same transition, but freezing the output from VIP to somatostatin at its ISO level. So you don't let VIP change, you let everything else change. And what you find is that the circuit stays at the ISO level. It takes a little transient and comes right back and stays at the ISO point. This is the cross point. And so when you look at the response changes or the change in input, there just isn't much. So the change in VIP is necessary for the change from ISO to cross. It's also sufficient because if we don't change layer 4, we keep layer 4 in the iso state, but we change VIP to its cross level of input to somatostatin, then you get basically the same transition. It happens a little bit differently. There's a bigger non-monotonicity in the somatostatin response, but it goes to about the same point on average. And again, so now you know that this was driven by the VIP-SOM disinhibitory circuit, and yet you don't see much sign of it in the final input to excitation. In the final input, you mostly see a change in the excitation. So the disinhibitory circuit is responsible, at least in the model, for the change from iso to cross. It's necessary and sufficient for it, but it's not acting as a simple feed-forward circuit. You activate VIP, you lower the inhibition to excitation. That's not what happens at all. It's catalyzing a change, which in the end is increasing the firing rate and therefore the recurrent excitation received by the excitatory cells. And so the prediction of this, okay, I'm over time, so I'll just say this predicted that if you silence VIP, you would retard that change from iso to cross, and the experiments indeed showed that. You can look at the paper to see this because I'm out of time. And I'm out of time, so I won't go through the summary. I will hope you just remember what I've told you. And I will stop there thanking the many people, thanking the many people who did the work, particularly Grace, Agostina, and Mario, and our funding sources. Thank you.